Okay, here's our second set of math notes for chapter 2. And this is our math notes that we're supposed to be listening to on September 5th and 6th. So we're going to look at two things in this section. One is how to generalize summation notation and use a shortcut, a formula for summation, so we can find things more easily, and also a review on how to add and subtract rational expressions, fractions that have x's and y's and things in them. So let's get started here. This is going over the story of the mathematician Carl Gauss. He was a famous guy that lived from 1777 to 1855. And the story goes that when he was just a young boy, he asked, his teacher asked the class to add up all of the numbers from 1 to 100. The teacher expected this to take a long time and planned to catch up on some paperwork. But Gauss, being a very bright math thinker, he found the sum in only a few seconds, foiling his teacher's plan. Gauss did not have a calculator like we have today, so he just figured out a logical reasoning way to solve this problem quickly. So what did he come up with? Well, what he came up with actually helps us with a problem like this. Can you imagine having to do this one by hand? This indicates that we need to go from 2 to 20 and find the sum of each of those, all the way the second, the third, the fourth, the fifth, the sixth, and so on, all the way till 20. So can you imagine doing this by hand? That this would take a long time. Well, let's take a look at what Gauss did with this and see if we can apply it to this. So what Gauss did was he took all of the numbers 1 plus 2 plus 3 plus 4 and so on, dot, 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 dot. And then he decided to sort of cut that list of numbers in half. If we cut it exactly in half, we'd go 1 to 50. And then he started drawing 51 and 52, 53, 54 backwards until he got down here and lined up 100, 99, 98, 97, and so on. Okay, so the cool thing about that is if you add every single one of these, you get 101. 101. 101. 101. So how many sets of 101 do we have lined up here? Well, there's 50 in the top row, 50 in the bottom row, so that's 50 groups of 101. So basically, we take 101 and multiply by 50, and we get the sum, 5,050. Is the sum of the numbers from 1 to 100, and that's what Gauss figured out. Okay, so let's generalize this a little bit. The first term in our sequence is 1. The first term. The last term in this sequence equals 100. So what Gauss did was basically add the first one together with the last one. So 1 plus 100, that's where we got our 101. First plus last. And then he multiplied by half the number in the sequence. So if there are n in the sequence, you divide that by 2 and multiply that. And there you go. You've got the sum. So how about we apply that over here? What's the first term in our sequence? Well, the first term here would be 2 times 0.01, and so that would be 0.02, and then plus 1.7, and so the first term would be 1.72. And what would be the last term? If we multiply this times 20, 20 times 0.01 would be 0.2, and 0.2 plus 1.7 would be 1.9. So what we have here is the first term in the sequence plus the last term in this sequence, and then we're going to multiply by how many terms are in the sequence. Well, how many are there from 2 to 20? Well, if there were 2 to 10, it would be 2, 3, 4, 5, 6, 7, 8, 9, 10. There would be 9 of them. So the number of terms in this sequence is 2 to 20, so I'm thinking there's 19 of them. And then we divide that by 2 because we only need half, just like we did over here. So calculate all that, and we have our sum. So 34.39 ends up being the sum of this crazy sequence. All right, so let's make a general rule here. So if we've got some number into let's say our let's see, the sum of k equaling, say, 1 to n, we're not sure how many numbers in our sequence, times some rule, some function, and we want to find the sum of that. It's always going to be the number of terms in the sequence n times our first plus our last divided by 2. And that's the formula for that. There's more formal ways to write that, but I think that's good for now. Okay. All right, moving on to a review of addition of rational expressions. So this is the example of what I mean by rational expressions, where we've got fractions that have x's and things. Well, when you add rational expressions, in other words, fractions, you must have a common denominator. Remember that? So what we typically do in when we're trying to find how to add fractions is sort of like it makes a bow tie shape in what we do. Because basically, if I've got b and d as my two, I need to multiply this one by d and this one by b, and we get this sort of pattern going on. So let's give this a try. Let's say we start with a over b plus c over d. Well, I need this denominator to be bd, so I need to multiply this by d over d, and I need to multiply this by b over b. So we end up with our AD plus CB over BD. And that's what's going on here, that sort of pattern. So let's see if we can see that pattern in this problem here. So we're multiplying this one, x minus 1, times the top and the bottom over here. And we're multiplying the x plus 2 times the top and the bottom over here. And what we end up with is our common denominator, the 2 times the x minus 1 and the 3 times the x plus 2. And then we simplify by distributing and then combining like terms, and there we have our final. So let's try to apply that to something. Let's apply it to this problem here. So my denominators are not currently the same, and subtraction and adding, same thing, we need to have a common denominator. So I'm going to multiply this on the top and the bottom here. And so I end up with 6 times x minus 2. And then minus, I'm going to multiply this over here, 4 times x plus 2, all over the common denominator, which is these two multiplied together, x plus 2 times x minus 2. So now we need to simplify this. So let's distribute the 6, and we get 6x minus 12, and distribute a negative 4, so we end up with minus 4x and minus 8. And this is all over what we had as a denominator before. We don't need to multiply those together at this point. Let's combine our like terms. We end up with 2x minus 20 over x plus 2 times x minus 2. Then it's always good to see if there's anything that will simplify. If I divide 2 out of both of these, I will have 2 times x minus 10. Well, x minus 10 doesn't cancel with either of these, so this is pretty much it, and we're done. Okay, we're going to practice this in class next week. So be ready to do that. I'm going to want to see what you know how to do. Okay, that's it.